Okay, so this afternoon I'm going to go back through here. We have got this particular truss here that we still need to determine and calculate the internal forces on. Now we did the external forces or the reaction forces here in class today, so we need to go and figure out the internal forces. Now if you recall, up here the external forces, we did determine that R of CY equals 750 pounds, and it was in the positive up direction. RC of X was going away from joint C, and that was at 1,500 pounds. Because it's going in that direction, we can say that's negative 1,500 pounds. We had R of A in the X was at 1,500 pounds as well, and that was going to the right, a positive. And that leaves us with some remainders here as we figure this out. Now, real quick, I have drawn this truss, and we are using the method of joints to determine the internal or tension compression that are actually on this particular truss. And what we're determining here now is we've got members BC, members AB, and members AC that are the actual trusses. Now, we are talking, and when we do this, we assume that each of these members are in tension. That means they're being pulled apart, they're in tension. And we draw the arrows on our free body diagrams as such. So you have to think about it in this term. Here we have member BC, and it's attached at the joint. So if this member is being pulled apart and in tension, there's an equal and opposite force at the joint that is acting in the opposite direction of the force pulling it. So this is one of the reasons why our arrows here, and we're assuming, when I say we assume that it's in tension, the members are being pulled that direction or that way, lengthwise. This is the reason why our arrows are pointing away from the joint, because it's the force of the joint pushing back on the member as tension forces are being there. Now, we're going to find out, though, obviously on a truss, not all three of these members can be in tension. We just assumed that at the beginning to help us with our math, and we're going to find out here which one of these are actually in tension and which ones there are not. So we've got our joints, and we're using the method of joints, so we got our free body diagrams. Now I've already kind of done those free body diagrams, but we'll do it real quick again. So I'm going to do joint A here, and my free body diagram. I see something right away with joint A. So I got joint A. Notice I've got the force here of AC, so we'll label that F of AC, and we know that the force of R of AY is going into the joint. Now I drew this going the opposite direction, going the same direction. Now in reality, can we have two of these going that way? No, we've got to have an equal and opposite reaction. So force of AB is actually going to be going back towards the joint. But let's go ahead and let's make this assumption again for right now. We're going to see what happens with the math, and this is the force of AC. So we're going to do this, and we're going to work this out. So what we have here at joint A, here's our free body diagram, our FBD at joint A. So now all we have to do is the sum of the forces in the X and the sum of the forces in the Y. They all will equal 0. So sum of the forces in the X equals 0, and our forces here are R, AY, That's to the positive, plus F of AC, which is to the positive, the force of AC. Well, in order to get these to equal AC, we know our AY is 1500. So let's just go ahead and replace that with 1500 plus F of AC equals 0. We do our math here. F of AC will end up equaling negative 1500 pounds. Okay, so going back here onto our joint, this is actually negative. So we need to change that. So instead, what we found here was that AB is negative, so it is actually going the opposite direction. So let me do this big so we can see the difference. We assumed it was going away, but when we did our formula, it actually came out and showed us minus, so we see that it is actually going the opposite direction. So that's now the force of AC. I'm going to circle this here in this case. And again, the negative only implies direction. The actual force on this is 1500 pounds. It's just a negative because we're applying it in that direction. So let's go ahead. Now we have two others here to kind of determine. Oh, before I go on, we still got to solve the sum of the forces in the X. Well, here the sum of forces in the X, we only have F, the force of AC. Nothing else is acting on point A, which means that the force of AC is 0. There's no internal forces. AC here is 0. It is neither tension or compression. So now think about it in terms of this way. Now that we've seen down here that at joint A our force is coming in, that means that the force acting on the joint is pushing, which means that the force on here, AB, is going to be going the opposite direction of the way we assumed. So here, instead of this member being under tension, because at each of these points, this means that this AB, which we determined are here to be force of AB to be 1500 pounds, is actually in tension, or is it actually in compression. So we're going to mark that. This is compression. And now we also know over here at joint B over here that that is in tension and compression over here. So remember, equal and opposite forces, equal and opposite forces over here. So now we can choose. So we know AC, we can decide, are we going to go to joint C, or are we going to come over here to joint B to work next? Doesn't really matter. We can take a look and see which one we have solved most. Well, I know what force of AB is, and I know what the force, the applied force here on this member is, but I also know these up here. So it really doesn't matter which one you choose. So to determine what this actually is, let's go ahead and pick joint B down here. So let me go ahead and redraw joint B, my free body diagram. So I got BC here, my joint B is right here. I got 750 pounds. here. And of course we now know this force is the force of AB, this is the force of BC, and this is acting in that direction. And we know that this is 1,500 pounds. So, now, what I want to find is the force of BC. And in order to do that, I've got to break it up into its X and Y components. So, to do that, I'm going to come back here, and we're going to draw the X component, which is the force of BCX, and then the Y component, which is the force of BC and the Y. Now let me expand this out a little bit here so that we got some more room so we can really kind of see this. So we got the force of BC and the Y, and we've got the force here of BC and the X, and then we've got the force here of BC. So all of these are at point B. Now we got to determine what this angle is. So I got to step back for just a minute. I kind of missed this step. We got to see what this angle is here. And to do that, we're going to use trig. Now I've got here is the angle that we're looking for, theta. And I got the adjacent side here to theta, and I got the opposite side here to theta. So when we know that the tangent of theta equals the opposite side over the adjacent side. So I can redo this. Tangent of theta equals, opposite is 3 feet over 6 feet. Theta then becomes the inverse tan of 3 over 6, or 1 over 2. So let's go ahead and figure out for theta. Get our calculator out here. 1/2 decimal, that's a fraction, of course. We change that to the decimal. 1 divided by 2 equals 0.5. So that's our decimal. And then we take the inverse tan, and we see that theta here is 26.565 degrees. We'll keep those numbers for now, but we really wouldn't necessarily have to. But this equals 26.565 degrees. Here we go, 26.565 degrees. Now, again, I said we are going to use the X and Y components of the force on BC to get us information on the force of BC. And in order to do this, again, we're still using our sine and cosine functions. So again, the sine of theta equals the opposite over the hypotenuse. So let's plug and substitute here. So the sine of 26.565 degrees equals the force of BC and the Y over the force of BC. Force of BC in the Y then equals sine of 26.565 degrees force of BC. Okay, we're going to use this as a substitute. We also need to find the force of BC in the X to possibly use that. So let's again, now we're going to use the cosine of theta equals the adjacent, which is the force of BC in the X, over the hypotenuse, which is the force of BC. And again, as we do our algebra here, we find that the force of BC in the X equals cosine of 26.565 degrees force of BC. Now we're left with these two to possibly substitute in for the joint, especially when we start to come in and do our static equations. So we've got all of those now. We've got our force of BCY equals the sine of 26.565 degrees times the force of BC, and the force of BCX equals the cosine of 26.565 degrees times the force of BC. Let's go back to our free body diagram here. Sum of forces in the X equals 0. And the forces we have in the X are the force of AB, and in this case, minus the force of BC in the X. No other forces in the X. So we can substitute in now. So we know that the force of AB is 1,500 pounds. And we now know that the force of BCX is the cosine of 26.565 degrees force of BC. So, again, we do some more algebra here. So, we subtract 1,500 from both sides of the equation. We're left with negative 1,500 pounds equals the negative cosine of 26.565 degrees times the force of BC. Divide both sides of the equation by negative cosine of 26.565, so we end up with minus 1,500 divided by negative cosine of 26.565 degrees equals the force of BC. Well, now we can go ahead and do the math. Two negatives cancel out. Let's get our calculator in here. This is going to really become 1,500 divided by 26.565 cosine equals 1,677.05 pounds is the force of BC. And it is positive, so we know that that is in tension. So the force of BC now is 1,677.05 pounds, and this is in tension. So let's go ahead and put this back up here. 1,677.05 pounds in tension. And I'm going to just mark that with a T down here. Or compression here, tension here. We got 0. So we've now solved for all of the internal forces that are acting on this truss. So we got this member is in tension, our assumptions were correct. This member is in compression, our assumptions were not correct. If we want to double check, confirm our answer, we could double check and we could solve for joint C up here as well using the same formulas, and we would find that we end up getting the same value for member BC, but you can always use that just as a double check your math and make sure that it is the same thing. So this has been the method of joints and that we've used to solve this. So I hope this helps give you a little bit more understanding of what we're doing here as we solve and work out these different truss problems and learn how to do these and apply them. Thanks for watching.